Example 1 here on trig proofs asks us to prove that 1 plus cot squared a is identical to cosec squared a. So to start with here, again we're just going to be using some of the identities that we've already established. Well, in this case, the first thing that I notice here is we have a cot squared a here. Well, remember, cot squared a is written as 1 over tan squared a, and tan squared a can be expressed as sine a, or sine squared a in this case, over cos squared a. So this can be written as 1 over sine squared a over cos squared a. And well, in that case, that would leave us with simply cos squared a over sine squared a. So in that case, we can write cot squared a here as cos squared a over sine squared a. And the reason we're starting with the left hand side here rather than the right hand side is because we can't really do too much with the right hand side here, as it's just cosec squared a. In that case, we're going to start with the left hand side. Well, we can write that as 1 plus, as we've just mentioned here, cos squared a over sine squared a. And what can we do with this now? Well, what we could do here is get this over a common denominator. As we're adding 1 plus this fraction here, if we get this over a common denominator, this would be sine squared a over sine squared a. And this would be cos squared a over sine squared a. And all I've simply done here is multiplied this 1 here by sine squared a. Again, numerator and denominator, we don't write it, but underneath that 1 there is also another 1 there as a denominator. And because these are over a common denominator now, we can simply express this as one fraction. This is sine squared a plus cos squared a over sine squared a. And here now we can refer back to an identity that we already know, and that's the idea that sine squared a, so using sine squared a plus cos squared a identical to 1 here. So our numerator simplifies to just give us 1. And this leaves us here with 1 over sine squared a. And we can express 1 over sine squared a as cosec squared a there. Okay, which gives us the result there that we wanted to prove for example 1, giving us our solution. Example 2 here on trig proofs is asking us to show that the square root of 1 minus cos 2x over the square root of 1 plus cos 2x is equal to tan x. Now here again, we're going to start with the left hand side of this equation, because if we start with the right hand side, we're not going to get too far. We've just literally got tan x, so we can't do too much with that. However, this left hand side here, we can actually do quite a bit of work with this. So the first thing I'm going to do is just write this all under 1 square root here. So this can be expressed as the square root of 1 minus cos 2x all over 1 plus cos 2x. Okay. Now we want to show that this is equal to tan x. Now as we notice straight away, we have a cos 2x here in the numerator and a cos 2x in the denominator. We're going to be using our double angle formula for cosine. So therefore, if we write that formula out, cos of 2x can be expressed as cos squared x minus sine squared x. Okay. And in that form here of cos squared x minus sine squared x won't help us too much, but let's just have a moment here now to think about how we obtain this expression of tan x. If we're looking for tan x, what I would expect at some point is we make use of our identity of sine x over cos x gives us tan x. Okay, if we're looking for tan x as our solution here to this proof, then what we'd expect at some point is to be using this identity. And what I'm going to do here is make use of the fact that we can rearrange this double angle formula for cos 2x into 2 other forms. We can write this as 2 cos squared a, or 2 cos squared x here, sorry, 2 cos squared x minus 1. And we can also write this as 1 minus 2 sine squared x here. Okay, and we're going to use these two parts here now. So how would we use these two parts here? Well, if we think about it, if this is 1 minus cos 2x, if I replace that with this bottom expression here of 1 minus 2 sine squared x, we're going to obtain a positive sine squared x there in the numerator, or positive 2 sine squared x. Remember, what we're looking for is sine x as our numerator, cos x as our denominator. So that's how we know that we're going to substitute 1 minus 2 sine squared x into the numerator here, and then 1 plus cos 2x into the denominator. So in that case, substituting these in, then what we're going to obtain is the square root here of 1 minus 2 sine squared x, like so. And for our denominator, again, just substituting in this 2 cos squared x minus 1. So we have 1 plus 2 cos squared x minus 1. Okay. And here now all we need to do is start simplifying. Well, if we've got 1 minus 1, that'll just give us 0, and minus 2 sine squared x will give us positive 2 sine squared x. That's 2 sine squared x in the numerator. And in the denominator here, we're going to obtain 1 plus this minus 1, and again, that'll just simply give us 0, and that will leave us with 2 cos squared x there. Okay. Well, in this case now, we can again use this identity here now that we've obtained sin x over cos x gives us tan x. We can use it in this form here to simply obtain that this is going to be equal to the square root of tan squared x. Okay, so like we said, this is what we were looking to obtain, and we've done that perfectly. This gives us the square root of tan squared x, and in that case, if you take the square root of tan squared x, we simply obtain tan x there, which is exactly what we wanted to show here for our solution for example 2. Example 3 here for trig proofs asked us to prove that cos x is equal to cos of minus x. And here we have to think about this in quite a clever way. How could we express cos minus x? Well, cos of minus x, so cos of minus x, can be expressed as cos of 0 minus x. Okay, so cos of 0 minus x here. Okay. And that's quite a clever way of us expressing that, because now we can use our addition formula for cosine. So using, and again let's just denote this formula here, so using cos of a plus or minus b, we can express this as cos a cos b minus or plus sin a sin b. So writing this now, we simply use the fact that we've written cos minus x in this form of cos 0 minus x and extend that now using this formula here. So therefore, cos of 0 minus x will simply be written then as cos of 0 times cos of x. In this case, as we're minusing here cos of 0 minus x, we're going to be adding here. Okay, we correspond the symbols here, so that's minus. Means we're going to plus here. And that's going to be sine of 0, so sine of 0 times by the sine of x. And here now all we need to do is just simplify these products. Well, cos of 0 gives us 1, and cos x here will just simply give us cos x. That's 1 times cos x. Repeating this now with this product here for sine of 0 and sine of x, that's going to give us, well, the exact value here of sine 0 is just simply 0, and sine x is just sine x. And clearly if we do 0 times sine x, that will give us 0, and that's simply going to leave us with 1 lot of cos x, which is simply cos x there. Okay, which is exactly what we were looking to show here. So that gives us the solution to example 3. Our final example now on trig proofs is asking us to show that tan theta plus cot theta can be expressed as 2 cosec 2 theta. And here now again, let's just think about the left hand side and how we can express tan theta and cot theta. So tan theta can simply be expressed here as our identity that we're very familiar with at this point as sine theta over cos theta. And cot theta is simply the reciprocal of tan theta, so in that case cot theta here will simply give us the reciprocal here of sine theta over cos theta, which is simply cos theta over sine theta. So in that case now, if we just rewrite our left hand side using these two expressions, we obtain sine theta over cos theta, and then in that case plus cot theta, which is cos theta over sine theta. Okay. And again here, as we're adding two fractions, we just have to use our standard rules for fractions, so we need to obtain this over a common denominator. And we can simply do that by multiplying each fraction by the opposite denominator. So this left-hand fraction here, we're going to times top and bottom by sine theta, and repeat here for this fraction, but just changing what we multiply that to by cos theta. So therefore, what we obtain here is simply sine squared theta over, plus cos squared theta over the product then of sine theta and cos theta. So sine theta, cos theta. Well, here now, again, we're going to apply some basic identities that we're familiar with, which is sine squared theta plus cos squared theta gives us 1 here. Okay, so what that means is that our numerator here can be expressed simply 1. That gives us 1 over sine theta cos theta. And 1 over sine theta cos theta, we're actually getting very close now to what we want to show here. Notice this is 2 times 1 over sine of 2 theta. So that means we're going to use our double angle formula for sine. So if we write that out here, sine of 2 theta can be simply expressed as 2 sine theta cos theta here. Okay. Well, in that case, if we want 1 over sine of 2 theta, all I'm simply going to have to do here is times this by 2. Okay, so times top and bottom by 2. If we times top and bottom by 2 here, what we obtain is 2 over 2 sine theta cos theta. So 2 sine theta cos theta here. And then in that case, as we've just noted, 2 sine theta cos theta is simply sine 2 theta. So this is 2 over sine 2 theta. And you can know here straight away that this is 2 cosec 2 theta. If you're not too sure why this is 2 cosec 2 theta, split this fraction up as 2 times 1 over sine 2 theta. Okay, and then in that case you simply obtain 2 times cosec 2 theta there. Okay, which gives us the solution there for example